I think the first thing I'll do is announce what the schedule will be for the next, for this week and next week. Today, of course, I'm going to try to finish the main points of this graphical method called the McCabe-Thiele method for calculations and ideal stages for fractional distillation. Tomorrow, for the laboratory period, as I had indicated, I would try to arrange a field trip, which I have. So we're going down to, we'll try to leave as many as can go at 1 o'clock to Lodi to visit the central cellars of the Guild Wine Company, particularly to see the brandy warehouses and the brandy processing operations. And then probably a quick tour through the wine cellar and wine bottling operations. And then we'll go over to the Bear Creek cellars of the Guild, where they're still, as I understand it, still distilling wines into brandy, and see a couple of distilling units operating. And we'll try to aim for getting back by 5 o'clock, but the likelihood of getting here before about 5:30 is not so good. So those of you who have that tasting period, I think the arrangement's been made that you can taste even if we're a little bit late for that 5 o'clock tasting, wine tasting section. So tomorrow morning at 8 o'clock lecture, I will have I think I'll devote it primarily to steps in production of brandy, and a few comments of orientation nature before we go on the field trip. And then there will not be any laboratory period from 9 to 12. Hope as many as possible of the morning laboratory section can arrange to go on the field trip. And then on Thursday I'm going to discuss in general production methods for whiskey and grain spirits in the United States. Perhaps with some brief reference to differences between that and, let's say, the Scotch methods used in Great Britain. Next week I'm going to be gone, but I won't let you off. On Tuesday next week, 30th of October, Professor Mike Lewis will be your guest lecturer, and he will discuss, be lecturing on malting and fermentation, particularly on the difference between distiller's malts and brewer's malts. Now, those of you taking his course may find some duplication, but I don't think it'll be very much, because it'll be from a different approach. So that's the reason I'm going to precede his lecture with mine about grain spirits processing, the outline of the steps. And on Wednesday, the 31st of October, Mr. Crowell will discuss with you brandy analysis, perhaps in general, and then concentrate on a couple of the more important ones that is applied to brandy. And the laboratories will be devoted to some practice in brandy analysis. Then on Thursday, the 1st of November, we'll have another one. We'll have an hour quiz, our second midterm. Pardon?
Thursday? Next Thursday?
Week from Thursday. In other words, 1st of November. So, and then I'll be back with you the following week. Well, what do you want? You do? Makes it harder exam. All right, well, it'll probably be open book then if that's what you want. All right. Well, now, before I proceed, are there any questions about the examination or the?
That was a problem. Well, they're coming up.
They're still circulating, I guess. Still circulating. Well, at the end of the last period, I had only a few minutes to refer to the handout, which is contained the technique of writing material balance relationships between the concentration of the more volatile component in the vapor and liquid phases on each tray, in terms of a general number, in terms of any tray number n in the rectifying section, and a corresponding term for the stripping section. So I just copied down those three equations again, but you've got them here in this handout. But the first relationship then was that y sub n is equal to L over V, y sub n plus 1 rather, is equal to x sub n plus d times x sub d over v. So we said that this is the equation of where y and x are variables, and meaning the concentration of the more volatile component, alcohol in most cases we're concerned with, on the two streams that are interacting on any particular tray, plate number n or tray number n. And so with this assumption that we made, this method is based on the assumption that the vapor and liquid rates flowing in a particular section of a distilling unit are constant, or in other words, independent of the tray number, if they're expressed on a mole basis, pound mole basis or gram mole basis, anyway, a mole basis. In which case, these are constants, so the ratios are constant, so this, and of course the distillate rate in terms of the vapor rate would also be constant. We're talking about continuous distillation now, where we have steady state operations. And of course the concentration of the distillate would be a standard specified value or a constant. So this is the equation of a straight line with these two variables in the form of a equation written in the form y is equal to mx plus b, where this would be the slope and this would be an intercept value. And so normally the reflux ratio will be something that will be stated, or we can arrive at some proper value, assume it, and so this becomes a constant. So we call this in the graphical application of this, we call this the operating line for the concentrating section. Second relationship, applying to the stripping section, so y sub m plus 1 is equal to L prime over V prime, where these represent the liquid and vapor rates on a mole basis in the stripping section. And they are normally different than these values. Sometimes one or the other might be the same, but in no case will both of them be the same as in the rectifying section. And so this is also the equation of a straight line of the same general form. We call this the operating line for the stripping section. Now, to locate those two lines on a graphical application of this method could be done if we know what these rates are, what these L liquid and vapor rates are in the both sections. And of course the concentration of the distillate in the bottoms would normally be a stated value or a part of the specifications. The point at which these two lines, well, first of all, I also pointed out that if you want to locate this line on the diagram, you first have the slope, and you have to have one intercept. Now you could do this by letting x equal 0 and solve for y, or let y equal 0 and solve for x. But if you let y equal y sub n plus 1 equal x sub n and solve it, you'll find that that the value of y then comes out to be x sub d. And so for this equation, if y sub n plus 1 is equal to x sub n, then it comes out to be that y sub n plus 1 is equal to x sub d, which says then, in other words, that the line passes through a value where y is equal to x of a value of the composition of distillate, x sub d. Or in other words, it passes through the diagonal at a value of x sub d. I'll attempt to draw a little illustration of this, and also I'm going to hand out one which is a little better plot of the one that than the one I'll be able to draw. Similarly, when y sub m plus 1 is equal to x sub m, it can be shown that this line passes through a value which is equal to x sub b, or the concentration in the bottom stream. Now, as an aid to finding what the slope is here, a third relationship is usually introduced, although it isn't absolutely necessary, but it is a sort of a simplification, which enables one to find the point of intersection of these two operating lines. And so that has the equation given on page 3 of this handout, what I call equation number 4 there, where it's written in the form y sub I is equal to q over q minus 1 times x sub I minus x sub f over q minus 1, where y sub I and x sub I represent the points of intersection of the two operating lines. And the Q is a factor which depends on the condition of the feed. Q depends on the condition of the feed. And let's say there's 2 or 3 ways to express it, but the easiest way for me to explain it, I think, is that Q is equal to the number of moles of saturated feed saturated liquid. And when I say saturated, what do I mean? Do you know what I'm talking about? What's a saturated solution?
Condense out in from the stage.
It doesn't have quite the same meaning that you talk about a saturated solution of a solute in a liquid, where it holds all it can. When we talk about the saturation temperature, we talk about it means the boiling point, or this may be a little bit of a misleading use of this term saturated, but we talk about a saturated liquid when it's right at the boiling point, but there's no vapor present. We talk about a saturated vapor as meaning a vapor that's in equilibrium with the liquid, but it's all vapor. Or in other words, at the conditions of the vapor given off from a saturated liquid, right at the boiling point. We speak of a supersaturated vapor or a superheated vapor if the boiling point of the temperature is above the equilibrium value or the saturation temperature. So in other words, when I say, in a distilling column when it's operating, we make the assumption that all the plates are at the saturation temperature. In other words, they're all boiling, but all the liquid is all at the saturation temperature. And so, think of it as boiling point if you want to. Number of moles of boiling liquid. Liquid at boiling point. Appearing on the feed tray resulting from the introduction of 1 mole of feed. So obviously, well, in other words, writing it in another way is that we say that L prime is equal to L plus QF. What does that say? What does this say? This says the liquid flow rate in the stripping section is equal to that in the concentrating section plus the feed multiplied by some factor. Understand here, if we drew a little cross section of a tray here where this is the feed tray, from the tray above we would have a liquid stream running down, which we call L. And so these two streams mix. And so what overflows to the tray below we call L prime. Well, of course, if the feed was a boiling liquid or saturated liquid, it would combine with this L, and then L prime would be L plus F, wouldn't it? For a boiling liquid. That means then, according to this definition here, that Q is at 1 for a boiling feed, if the feed was at the boiling point. In most cases, at the temperature lower than that. If the feed is at a temperature which is less than the boiling point, what's going to happen? At this feed point here, the vapor rising up here is going to be partly condensed to bring it up to the boiling point. Because you've got to have boiling conditions and vapor being evolved. And from the feed tray to continue on up into the concentrating section. So in that case, we would have a liquid stream somewhat greater than just the addition of feed, of the volume of the feed to that, the amount of the feed to that, because it condensed some of this vapor and it'd come back down as a liquid, you see. So in other words, we can say that we can write down a few limiting examples of what the numerical value of Q would be. Value of the Q factor. If we have a saturated or a boiling liquid, as a feed, then Q is equal to 1.0. If the feed is what we call a cold feed, or that is less than the boiling point, it may actually be partly preheated, but let's say it's only 150 degrees Fahrenheit. If it's alcohol water, it'll be less than the boiling point. So we usually talk about cold feed, but that's not a very good term. Let's say it's feed is less than the saturation temperature. Temperature is less than the saturation. Well, in that way, Q is some value which is greater than 1. The amount that is greater than 1 depends on how cold it is, or how much energy it takes to raise it up to the saturation temperature. Yeah?
Are you saying that if you're introducing boiling feed, that the whole lot of it will go straight down into the first tray of the dripping section, and none will go into the concentrating section? The Q equals
Well, and expressed as number of moles, as pound moles, that's right. We simply mix together the feed and the liquid, and what runs on down is L prime. And if this is a liquid at its saturation or boiling temperature, but there's no vapor with it, well, it will not change the amount of vapor passing on through that feed tray, because there's no energy necessary to be supplied to the feed. We could have the situation where we have heated the feed up to a point that's at saturation temperature, and then add some more energy to it, and we'd have a mixture of feed and vapor and liquid phase entering. See?
But when you're saying you're adding boiling feed, if you're assuming Q equals 1, that means the boiling feed's got no vapor pressure of the more volatile component.
It's saturated.
I say it's at the boiling temperature or the saturation temperature, but just before there's any vapor being evolved. We consider that no vapor has been given off. It'll give off its vapor as soon as it gets in on the tray where it interacts with more vapor, but it doesn't have until it gets inside the column.
I can take something up to its boiling point and have it not give off any vapor.
You have to add another bit of energy to it to produce the vapor. You have to add the heat of vaporization. We've added just enough heat to bring it up to 99.99% of the boiling point, let's say. It approaches 100% as a limit. In other words, you've got to add then what we call the heat of the vapor, heat of the liquid, or the sensible heat of the liquid, sufficient to bring it to the boiling point, but you don't add enough to create any vapor. You haven't added any energy equal to the heat of vaporization, which is very much larger, of course, than heat of the liquid. Well, perhaps this will be a little clearer in a moment or later, but anyway, suppose we had a mixed saturated liquid and vapor, which we could have if you ran the feed through a heat exchanger sufficient to bring it up to the boiling point, and still got more energy, like you might have a steam coil heater or a steam condensing steam heat on a heat exchanger. You could create a mixture of vapor and liquid and feed it in there. In that case, Q would have a value somewhere between 0 and 1. 0 to 1. In fact, we could completely vaporize it and make a vapor, saturated vapor. Well, all right. If the feed entering here is a saturated vapor, what would happen to it? It would not provide any liquid. It would provide an increase in the vapor, but it wouldn't provide any liquid. So Q, according to this definition, would be 0 for a saturated vapor. Now, if the feed is a saturated vapor, Q is 0. We could carry it on to another very impractical hypothetical state of a superheated vapor. Perhaps I'm sure there are examples in industrial distillation, such as petroleum and chemical technology, where there's vapor streams entering columns, and they may actually be superheated with respect to the particular column. In that case, then, if you had a superheated feed, it would not only all go in a vapor, but would also vaporize a little liquid on this tray, and so you'd have it's still a higher amount of vapor. So that, in other words, then Q would be negative, because according to the definition here, it's a number of moles of saturated liquid appearing on the feed tray as a result of the introduction of 1 mole of feed. Now, if that feed is a superheated vapor, you would end up with something less than the original amount. In other words, you'd have a decrease in the amount of liquid on the tray. In other words, in that case, L prime would be less than L. But normally we don't run into that. But let's say we had just to complete the picture, if we had a superheated vapor, in all cases I'm talking about here the feed conditions, superheated vapor, Q would be negative. It would be less than 1, less than 0. Less than 0. Well, so in other words, one would normally know what the feed conditions are. And so you can calculate this numerical value of Q and put in this little equation here, which again is the equation of a straight line between these two variables, so this slope and an intercept value, and locate that line on the diagram, and that'll tell you the point at which these two lines here intersect.
Yeah.
Well, I'm going to illustrate it now by drawing a diagram. That's probably better. You'll also notice that I've written on the top of page 3 that continuing from the bottom of page 2 where I wrote this relationship involving Q, that we can also write that V is equal to V prime plus 1 minus Q times F. or solving it for V prime would be equal to V that isn't the way I wrote it, but the way I intend to write on the sheet probably is that V is equal to V prime is equal to V prime plus Q minus 1 times F. Let me see now. Let me see how V prime. Well, if I solve this for V prime, bring this over on this side, and then change the sign of Q, well, then it becomes plus on the other side, right? Is that right? now, as a practical matter, or this, I guess I'll erase this and put it here on this. If we take a the equilibrium curve for a particular system, x is equal to y, the xy curve, and let's say we try to sketch in here the diagonal here for reference purposes. Didn't quite come out exactly. This is the x is equal to y line, the diagonal, which we always have occasion to refer to, or almost always have occasion to refer to. And we have some equilibrium curve. This is roughly what I'll call water curve looks like. And so, if we want to calculate the number of ideal stages it requires to separate a feed of a certain composition, let's say x sub f, into a distillate of some value x sub d, and a bottom stream of x sub b, the first step is to locate those values on the curve, on your diagram. And frequently, in its simplest case, we project those upward until they intersect the diagonal. Now, going back to what I said before, we normally start with, or a logical thing to start with in our graphical solution, would be to draw this operating line for the concentrating section. We said before it was a equation of a straight line intersecting in the diagonal at x sub d and with a slope of L over V. Now, for example, if I want to get the slope of that slope of the operating line in the concentrating section, and we'll just take a simple example. Say that the reflux ratio is 3:1. What I prefer to call the external reflux ratio. (3.0:1), which means that what this means is the reflux ratio is equal to the amount of liquid run back the top of the column divided by the amount of the distillate. Or in other words, we have a 3L for 1D. Now then, what I prefer to call the internal reflux ratio is equal to the ratio of liquid to the ascending vapor, expressed in pound moles or gram mole amounts. And this, of course, then would be equal to, since at the top of a column, the vapor given off here is condensed, and some of it's taken off as distillate, and the rest of it's run back as liquid. And V, of course, is equal to L plus D, because that's the only source of either both the liquid and the vapor, and distillate is the vapor that's passing off into the condenser. And so in this case, then we'd write that the ratio of here would be if let's say if D is 1, you let D equal 1, or then if let's say D equal to 1, why then L would be 3 plus 1, and the vapor, of course, would be 3. Well, okay, 3 plus 1. So L over V would be equal to 4 over 1, right? Or a slope of 8/10. or in other words, equal 8/10. So in other words, now we know enough to draw this line in here. If we know that the reflux ratio is 3 to 1 at the outside, which means that the internal reflux ratio is 0.8. So now you draw a line here with a slope of 8/10. Through this point here on the diagonal where x sub d intersect it. And now this has a slope of 1.0, x is equal to y. So a slope of 8/10 would be obtained by measuring over here 10 units, and up 10, or rather down 8 units and over 10. You locate some point over here and draw a line. Draw the line as far as you want. It may only be, it'll be terminate at some point in here, but we haven't located that point yet. Well, now that's the first step. This is the operating line. This would be the operating line for the concentrating section. And it is this same equation number 1 up here, equation 1.
Where did you get that, the slope equal to 8/10?
Yeah.
Where?
No,
You had L over D equal to 4.
It was 3/4.
Oh, wait a minute. Maybe I didn't. Be 3 over 4, excuse me, it'd be 0.75. I'm sorry, I did make it wrong. L over V. In other words, if I said the reflux ratio is 3 to 1, it means 3 liquid for 1 D. So the vapor would be equal to 4. So L over V would be 3 divided by 4, or 0.75. I'm sorry, I didn't put the right value down. If you had 4 to 1, external reflux ratio, then the internal L over V would be 8/10. 4 over 5. Yeah?
If L over V is equal to 3/4 for x sub b, why do those two equal?
Why is what equal?
I'm sorry.
Oh, okay. So we have this drawn in here now. Now the next point would be to locate this one here, but we don't know where it's going to intersect. We know the operating line here for the stripping section passes through this point right here, but we don't know exactly what the slope is without calculating these values of L prime over V prime. Well, we could do that, but we involve the same principles that we do to calculate the numerical value of Q. So in a moment I'll give you a handout which will illustrate how you calculate Q for a particular value of where the feed is cold. But let's take the simplest case now and assume that our feed is saturated feed at the boiling point where Q is equal to 1. All right? If Q is equal to 1, then the slope of this Q line, which I erased the formula for it here, but the slope of the Q line, or that the slope of the Q line has a value of what? That equation I gave you. Q over Q minus 1, right? Okay. Q divided by Q minus 1. Well, now if Q is equal to 1, well, then the slope Q over Q minus 1 would be equal to 1 over 0, which would be infinity. Infinite, which means it's a vertical line. So in other words, all we have, and we've already indicated that it passes through a value on the diagonal equal to x of f. And so we just project the line up vertically here. And this would be the Q line. This would be the equation of the Q line for a saturated feed. That is, Q is equal to 1. And so that establishes the point of intersection of the two lines, of the two operating lines. So all we have to do then is draw in this equation here for the stripping section through that point and the intersection with the diagonal. And so we have our operating lines drawn in. We have the so-called McCabe-Thiele diagram constructed, ready to count off the number of steps required. Now you can start at either end. We can go from here to count the number of steps to go up to the feed concentration, which would be the number of trays needed in the stripping section, and then count the steps on up to get to the distillate concentration, which would be the number of ideal stages in the concentrating section. Remember that we make the assumption that the vapor evolved from a particular tray is in equilibrium with the liquid on that tray, or in other words, Y sub n is in equilibrium with X sub n, or Y sub n plus 1 is in equilibrium with X sub n plus 1. However, so that any point on this curve, of course, represents equilibrium conditions, so it represents the composition of the vapor given off from a given liquid on that tray. But these equations here represent the relationship of the vapor from the plate below a given liquid tray, a given liquid, or the vapor rising up and interacting with it. Well, anyway, in a practical sense, then, you just draw right angle steps. Because if you had this concentration on the bottom, not the bottom tray, but the bottom liquid, the pot, so to speak, down below the bottom tray, the vapor that had been equilibrium with it would be obtained by projecting up to the equilibrium curve. Now, if you go right angles across here, you get the concentration, or this would be this represents then the vapor given off from the base, or from the bottom, or not the bottom tray, but from the pot down at the bottom. This is the composition of vapor. Now that's interacting with the liquid on the first tray. And so this would be the concentration on tray number 1 of both X and Y. This would be well, it's called X sub 1. So in other words, it shows you that we increased the concentration by that much by going from the pot to the first step. To go up to the next step, just repeat the process. Repeat the process. This is a projection of that line, so we don't want that in here right now. All right, now, so see the way I've drawn this, it doesn't come out quite to hit this value here. So in other words, you can still treat it as a fraction of a step, like this is about 4/10 of a step to go from this tray here to this here. In reality, since a lot of in real situations, we may have 10 or 20 different steps in here, so missing it by half of one really doesn't affect the answer very much anyway. But when you do have only 2 or 3 trays like this simple example I'm drawing here, well, then you simply estimate the fraction of a step of an ideal step. So you continue the stepwise operation. So this particular one happened to come out almost exactly there, but it could have come out there. It would have been another fraction of a step. So this says then that for these particular operating conditions, which establish those slopes, these are the number of steps required to go from the bottom composition up to the feed composition, and these are the number of steps to get on up to the distillate composition. I got a couple handouts here which I don't have time to go into, but
That doesn't have to work out exactly. You have to, if it doesn't work out, then you just take a percentage of that step.
take one of these and pass it along. And take one of these and pass it along. If I can just take about a minute to explain these two handouts, and then we'll stop. The first one is a copy out of a commercial solvents manual that we referred to, and you can see the original reference down at the bottom here. And it's an enthalpy or heat content for ethyl alcohol water solutions. In the left-hand side of the table, it gives it as a function of percent alcohol by weight for various temperatures. In the right-hand part of the table is for boiling solutions, or what we call saturated solutions. Percent alcohol by weight and the boiling point in degrees centigrade. And then the enthalpy, or the heat content of the saturated liquid, and then of the saturated vapor. Of course, the difference between the saturated vapor and the saturated liquid would be the heat of vaporization for the mixtures. So there it is, right there. Perhaps I ought to take time to explain what a BTU is, but anyway, well, briefly, it's the amount of heat necessary to raise 1 pound of water 1 degree Fahrenheit, just like a calorie is equal to the amount of heat necessary to raise 1 gram of water 1 degree centigrade. Maybe have a little bit more precise definition than that, but for all practical purposes, that's it. So in other words, and the enthalpy is based on essentially on water having zero, at 0 degrees centigrade having 0 in heat content. The reference state we take is 0. So it takes 180 BTUs roughly to go from 32 degrees Fahrenheit up to 212. 212 minus 32 is 180, so almost, so it comes out to be 180.1, you see there. Then the second page is a table which is somewhat based on this table I prepared, which takes some of those same values, but you see over in the right-hand column, the last column, is the molal heats of vaporization, or the on a mole basis. And I told you I was going to bring something to justify this assumption. Well, you see there that all from 0 up to 100%, the maximum heat of vaporization is about 17,750 BTUs per pound mole, and the minimum, which is for pure alcohol, is 16,990. So all of them lie almost within a 200 or 300 BTUs per pound mole of 17,000. So you see it's sufficiently constant that we can make this assumption of equal molal heats of vaporization. Well, the second handout is simply a little summary of much of what I said. It's a summary of practical steps, and you can go through that. Here's a resume of the top things I made about the Q and Q line, and on the third page, an example of how you calculate it using these tables of enthalpy I gave you on page 3 of this handout. For example, here's one here which the feed temperature is 100 degrees and 10% alcohol by weight. It comes out to be that the heat is such that the Q has a value of about 9.95. And finally, the last thing is a copy out of Brown's book of a McCabe and Thiele plot showing a little bit more clearly and a little more detail what I just tried to show here in schematic form. Okay, that's all this morning.